and we just check the distance between 2 points. Every the 1 point with each point. So we check all the points. So here we have this algorithm. So here we initiate the D with infinity. Then here find distance between two closest points in the plane by brute force a list of p n greater than 2 points. So I have 2 points, p1 x1 y1 until pn xn yn. Output the distance between the closest pair of points. So here d infinity for I equal 1 to n minus 1, j for j I plus 1 to n. Here we find the minimum. So we compare each point with the other points. So d equal the SQRT. So means the this is the SQRT xy minus xj y minus yj the square root. So it will give me the distance with this one. Okay. So this is how to use brute force to find the divide and conquer. Divide to find the closest pair problem, solve closest pair problem. So using this algorithm. Now here we go to how to solve it in divide and conquer. In divide and conquer, what we have to do, step 1, divide the points given into two subsets S1 and S2 by a vertical line x equals C. We call it the median. This one equal x equal C. So the half of points lie on the left or on the line and the half the points lie on the right of the line. So here we just make a median. So roughly we can say that half of points will be on the right side of the median, and the half of the points in the middle and on the left side of the median. So then what we have to do, the question here appears. So here we find the closest pair. We find also make the median in this, and recursively we make the median here. So until we find the closest pair. So assume that D1 is the closest pair in this part. D2 is the closest pair in this part. So D1 is in the left side and D2 in the right side. So we have to see. So here maybe we have three possibilities. Maybe the minimum distance is in the left plane on the left side of this plane. Maybe on the right side of this plane. Maybe point from the left side, point from the right side. So in the middle here. So point from here and point from here. From one point from the left side and 1 point from the minimum, from the right side. This is the three possibilities. Again. So here after we make the median, so in this part maybe will be the closest pair. Okay, mean the minimum D between two pairs. So and maybe and here for the maybe it will be here in the left and the right side of the plane. Okay, and maybe here the pairs are distributed between the here the point in the left and 1 point in the right. So here we will find 1 point and here and 1 point here, and this will be the closest pair. So how to overcome this problem? We will see here step by step what I'm going to do. Find recursively the closest pair for the left and right subsets. Set D minimum D1, D2. So here we find the closest pair in the left side and in the right side, and we can limit our attention to points in the asymmetric vertical strip of width to the 2D as possible closest pair. Let C1 and C2 be the subsets of points in the left subset S1 and of the right subset S2 respectively that lie in this vertical strip. The points in the C1 and C2 are stored in increasing order of their y coordinates, which is maintained by the merging during the execution of the next step. Step 4, for every point Pxy in C1, we inspect points in C2 that may be closer to P than D. There can be no more than 6 such points because D is less than D2. So I will explain here in details what is going on in this closest pair divide and conquer. Let's go to the algorithm first. So the algorithm, it says? It says that here we have C1, C2, and these 6 points. What is the 6 points? Let us go through this algorithm. Efficient closest pair PQ. Okay. So solve the closest pair problem by divide and conquer. Input an array P on n greater than equal 2 points. So here at least we have 2 points. At least we have 2 points in the Cartesian plane stored in non-decreasing order of their x coordinates. So here they are stored in non-decreasing order of their x coordinates, and the array Q of the same points stored in non-decreasing order of the y coordinates. So here we have the y coordinates and the x coordinates. So here this is the how we manage first before we start. So the points in the Cartesian plane stored in the non-decreasing order of their x coordinates, and the array of Q same points stored in the decreasing order of the y coordinates. Output Euclidean distance between the closest pair of points. Okay. So here we have first, if n less than equal 3, means we have only 3 points. We go using what we use, brute force algorithm. So here we have to have n greater than 2, means at least I have 2 points. And if it is less than 3, this is the algorithm said. If I have only 3 points, I will do it using brute force algorithm. What does it mean using brute force algorithm? Means check the distance, this one, using this algorithm. D equal infinity, I equal 1 to n minus 1, j equal I plus 1 to n, d minimum xurt x1 minus xj power 2 plus xi minus xj power 2. This is square root for this for the Euclidean distance. This is using brute force, 10d. This is what is the case if we have here n less than equal 3. Else copy first n. So here I divide the points into the plane into areas. Here, points P array P left. Copy the same P into to from Q to Q array Q1. Okay, and copy the remaining into points of P to array PR, and copy the same in divide by 2 points from Q to array QR. So here we have P left, Q left, and we have P right, Q right. Okay, so here we have the points. We make the like a median. Okay, so copy the first n divide by 2 points of P to array P left, and copy the same n points from Q to Q1 left, and n 2 points for P to array PR, and here points QR, Q left. D1, DL, efficient closest pair, P left, Q left. So then I call again the recursively the algorithm. So when I will stop here. When the points are less than 3, I will return here D according to the brute force. And also I will call the right efficient closed pair PRQR. So here I will call this one and divide all the plane in left and right, left and right, left and right, left and right, until I find the here minimum. Then here I say D equal minimum D left DR. So minimum means give me the minimum value of distance left and distance right. M equal, this is the median. So here m n divided by 2 minus 1 dot x. Okay, here I will get the here I will get the median m. So this is the line which we are going to divide the plane into two parts, into two left and right. So how I will divide it? Using m p, number of the points, divided by 2 minus 1 dot x. Copy all points of Q for which x minus m less than d into array S0 num minus 1 d minimum square d power 2. Okay? For I equals 0, num minus 2, do ki plus 1, another loop here, while k less than equal num minus 1, and sk dot y minus si dot y power 2 is less than d minimum square. Here d minimum square equal minimum square sk dot x minus sy x power 2 plus sky minus si y power 2 and the minimum square. So here I find the minimum square. Then here k equal k plus 1 and return sqrt the minimum square. This is the algorithm, but how we are going to see what is going on. So in this algorithm, what we are going to do, as I told you, here first I have to do this division of plane. Then I find the minimum D1, D2. We can limit our attention to the points in the symmetric vertical strip of which 2D as possible closest pair, let C1 and C2 be the subset of points in the left subset S1 of the right subset S2, respectively, that lie in this vertical strip. The points C1 and C2 are stored in increasing order of their y coordinates, which is maintained by merging during the execution of the next step. For every point x, y in C1, we inspect points in C2 that may be closer to P than D. They can be no more than 6 such points because D is less than D2. So here, what does it mean here? Let me explain to you using the here when I find Here I apply D1, D2. So I just try to check what is the distance here. So I notice that D1 here and D2 here. And then I fix the minimum to the minimum value between two closest pair equal D. So then I make here on the median. So I make D 2D. We call it 2D. D for to the distance to the right and D from the median to the right 2D, and here also 1D. The height is 1D. Then I will have the points. Okay, and maybe the points is here. So here I will draw line. So it will cross 1, 2, 3. Then I will draw a line here. Okay, it will go 1, 2, 3. So here this line. Okay, this is the line, and here it will be the points that is said 6 points. So here it will be 6 points, and we cannot D cannot be more than this 6 points. So here we have D, and the closest one maybe here D. Okay, D, and the height is D, and here the length is 2D. Okay, and here we have to check whether we have points in this box. In this box, okay. So we divide the box here, this box D, and we divide this box in four parts. Four parts. So here we have we get the 6 points. So any points cannot be more if we compare it with this one. So here there cannot be more than 6 such points, because here there is no. I will check with these points if there is points here in this box in this box. Okay, let's go through the here to the let me to the book. Divide and conquer. The closest pair problem by divide and conquer. So the closest pair. This is I'm reading from the book that I have sent you. I already sent you the book. So here we have discussed that brute force approach to solving two classic problems of conventional geometry, the closed sphere problem and the convex hull problem. We show that the two-dimensional version of this problem can be solved by brute force algorithm, and it will take theta n power 2 and theta n power 3 time respectively in this section. So here we have this problem will be solved by theta n power 2. We discuss more sophisticated and asymptotically more difficult algorithm for this problem, which are based on the divide and conquer technique. The closest pair problem. Let P be a set of n plus greater than 1 points in the Cartesian plane. For the sake of simplicity, we assume that the points are distinct, and we also assume that the points are ordered in non-decreasing order of their x coordinates. If they were not, we could sort them first, by an efficient sorting algorithm such as merge sort. So first thing, the points should be in non-decreasing order, in ascending order. If it's not in ascending order, we use an algorithm to make it first to be sorted in non-decreasing order or ascending order. Okay, this is the first condition for first step here. If it is not in the it is not in non-decreasing order, meaning in ascending order, I will make sort. Okay. Then it will also be convenient to have the points sorted in the separate list in non-decreasing order of the y coordinate. So then I apply first x coordinate, then y coordinate. So this is the condition of this to for the closest problem. The y coordinates we will donate such as a list Q. So we have P and Q. If n less than equal to and 3, the problem can be solved by the obvious brute force algorithm. So if number of points between 2 and 3, as we said that at least we have 3 points, then I can find the closest pair. The closest pair. So at least I have 3 points. If I have 3 points, I will use brute force. More than 3, okay, I will use divide and conquer. If n greater than 3, we can divide the points into two subsets, P1 and P left and P right of n power divided by 2 and n more than 2 points respectively. So here we divide the median, so half of the points in the left and half of the point in the right. Okay. By drawing a vertical line through the median m of the x coordinates, so by x coordinates, so that n divided by 2 points lie to the left of the or on the line of itself, and n divided by 2 points lie to the right or on the line. Then we can solve the closest pair problem. So here, this is the problem here. Vertical, we have a vertical line, and here in the right plane or on the median or left plane on the line. Okay, that's the box that I just was discussing here. I will go through it here. This is the median, and this one D1 and this one D2. So here the dimension of these boxes is 2D, and this is the box of D. So idea of the divide and conquer algorithm for the closest pair of problem: rectangle that may contain points closer and D minimum to point P. Okay, I said maybe D1 is here, means D2 DR here, D left, and D left here. So maybe the pair from the left side, or maybe the pair in the right side, or on the left side, the two pairs. Maybe the pairs, one on the right and one on the left. This is the three conditions that we have. That the stage three. I think three cases. Three cases. Okay. So recursively of subsets P left and P right, let D left DR be the smallest distance between pairs of points in P left and PR respectively, and let D minimum PL minimum D left DR. Okay. Note that D is not necessarily the smallest distance between. Okay, note that D is not necessarily the smallest distance between all of the points paired because points of the closest pair can lie on the opposite side of the separating. Okay, this is the case. Note that D is not necessarily the smallest distance between all points pair because points of the closest closer pair can lie on the opposite sides of the separating this line. Therefore, as step of combining the solution to the smaller problem, so yeah, therefore, as a step combining the solution to the smaller subproblems, we need to examine such points obviously, we can limit our attention to the points inside the symmetric vertical strip of width 2D around the separating line, since the distance between any other pair of points is at least D. Okay, so this is the 757A, and this is the distance. So here we have D is not necessarily the smallest distance between the points pair because points of the closer pair can lie on opposite side. I mean, one side left, one side right of the separating line. Therefore, as step of combining the solution to the smaller subset of points, we need to examine such points observably. We can limit our attention to the points inside the symmetric vertical, inside the symmetric vertical strip, okay, of width 2D around the separating line, since the distance between any other pairs of points at least D. Here we have D and D. Okay, what is D? D is the membrane D left and D R. I make here a box with the around the median with 2D, and the height is D. 2D and the height is D. Now, let's S be the list of points inside the strip of width 2 around the separating line obtained from Q, and hence ordered in non-decreasing order of their Q coordinates. We will scan this list, updating the information about D min, the minimum distance seen so far. If we encounter the closer pair of points, initially D min equal D, and subsequently D min less than equal D. Let here. This is the points. This is the points that I'm talking about. Okay, this is the points that I'm talking about. So here, this is the distance between the points here. So we have points is in this area, and we have point this area. We find the right and the left, but here we will find between this. So here, okay. So S will be the points inside the strip of width of 2D. So this is the 2D, and this is the points in the separating around the separating line obtained from Q, and hence order in non-decreasing order of their Y coordinates. This time coordinates, we will scan this list, updating the information about D minimum, the D minimum distance seen so far. if we encounter a closer pair of points initially, d min equal d, and subsequently d min less than equal d. Let p x y be a point on this list. For a point p dash x dash y dash to have a chance to be close to p and than d min, the point must follow p on list CS, and the distance between their y coordinates must be less than d minimum y. Okay, here he's asking why. He said that the 2 points here, the distance cannot be here more than d. Okay, cannot be more than d, because if it is here, it will become the left, or the right, or it will become the left. So here, so we have point xy, okay, on the list for a point p dash x y x dash y dash, our chance to be closer p than minimum. So maybe I have a points, one on the right side and one on the left side. So here what I'm going to do, for a point p dash x y dash to have a chance to close the divider, the point must follow p on the list p, and the difference between their y coordinates must be less than the minimum. So here, geometry, geometrically, this means that P dash must belong to the rectangle shown in 5-7b. This point, this point, why it comes like this? So it will become like this. This is the point P. This is the 2D. Okay. This is the D minimum. The D height also. So now, what he said, geometrically, this means the B dash must belong to the rectangle shown in figure 5.7b. The parameter inside exploited by the algorithm is the observation that the rectangle can contain just a few such points because the points in each half, left and right, of the rectangle must be at least distance d apart. It is easy to prove that the total number of such points in the rectangle, including P, code does not exceed 8 problem 8 problem 2 in the section exercises. Here we have this is in problem 2. We will find how it was not does exceed these 8 points. Here in this selection, a more careful analysis reduced the number to 6. So here we have some of them they said 8, and some where they said 7, and some they said 6. So what does it mean? we have 1, 2, 3, 4, 5, 6. Some of them they have make it 8. 1, 2, 3, 4, 5, 6, 7, 8. So they make it 8 points. Some of them they make it 7. They said 1, 2, 3. They make it like this, and also minimize the rectangle in multiple squares. Okay. A remote careful analysis reduces this number to 6. Thus, the algorithm can consider the algorithm can consider more than 5 next points following P and the list S before moving and the list S. So here, thus the algorithm can consider more than 5 next points. So here, what does it mean? I find these points these points I have these points, assume P1, P2, P3, P4. So I will compare each point with the 5 points coming after this. Or some of them they said compare the 6 points. Some of them said compare the 7 coming points. Some of them said coming compared to the 8 coming points. So here I compare the point with the what is the coming point. So 5 coming point, and some of them say 6, some of them say 7. I compare this point with the next points and check if there is what is the distance. So here, thus the algorithm can consider no more than 5 next points. Here, why he said 5? That he said there is only 6 points. The point, and you have 6 points around the rectangle. Around the rectangle, we have 1, 2, 3, 4, 5, 6. That's why he said we'll compare with 5 points. 1, 2, 3, 4, 5. Some of them they said we'll also make here the D is more broken in small squares, and then we'll have the the points in the median. So here, thus the algorithm can consider no more than 5 next points following P and on the list S before moving up to the next point. Here is absolute code of the algorithm. We follow the divide given in section 3.3 to avoid computing square root inside the incremental loop of the algorithm. Okay, this is the algorithm. What the algorithm said here, as we said, we follow the device given in section 2 to avoid computing square root inside the innermost loop of the algorithm. Innermost loop of the algorithm. Yeah. This is the algorithm efficient closest pair PQ. Okay. Here we already go through this one. We divide the points in Q left and P left and P right and Q left and Q right according to the X order x coordinator and y coordinator, while it has to be in uh, non-decreasing order. Output Euclidean distance between the closest pair and the closest pair D. So here, return the minimum distance found by brute force if less than 3. Here, else copy here we differentiate between P left and P right. Okay. D left is our efficient closest pair. P left PQ. DR equal efficient closest pair BR PQ. And here we have minimum D1, DL, DR. Okay. So here n equal n divided by 2 minus 1 multiply x. Copy all points of Q for each x minus n less than d into array is 0 n minus 1 dimension square d power 2. For I equal 0 num minus 2, I equal I plus 1, while k less than equal num, and sky sy the distance is less than d minimum square. Here we have d minimum square will be minimum square x power 2 plus sky minus y power 2. I make the minimum of these two by get the square root. Here we have the minimum square. Okay. Okay. The algorithm spends linear time both. Here, analysis of the dividing problem into the two problems have the size and coordinates obtained solution. Therefore, assuming as usual that n is of a power 2, we have the following recurrence for the running time of algorithm. This one, how to study the complexity of the algorithm. So we have 2 n power 2 fn. Here a equal to, b equal to, d equal to. Why we have t n power 2 n here? Because here we have t n minus 2, t n 2 divided by 2, and t n divided by 2. So this is the complexity why we have here 2 t n plus f n, where f n limit n applying master theorem d equal 1. So here the overall efficiency class is storing is done by O n log n algorithm, such as merge sort. In fact, this is the best efficiency class one can achieve because it has been proved that any algorithm for this problem must be omega n log n under some natural assumption about operation algorithm can perform. So let us get an example. So here convex hull, this one problem you will study it at the here last the convex hull problem, and star-cell matrix multiplication. This is you study by yourself. Okay, self-study for star-cell matrix multiplication, and where is convex hull problem. Okay, so here I will try to find now paint. Okay. Before I start the example, let's take 10 minutes break, then we continue. Okay. Okay, let me here first write the exercise, then we can go through it. So here P Q. Okay, now is the algorithm. Okay, now we have this is the algorithm, and this is the pairs. Please start solving this question. I will give you 10 minutes to solve this one. So who wants to share this answer? Or stop sharing. Let me someone try to solve it together. We solve it together. Who wants to try? Any volunteer wants to try? Okay. So here we have these points. Okay, here one, two, three, four, so extra, 1, 2, 3, 4, 5, 6. And here we have 1, 1, 2, 3, 4, 5. So first point, 1 and 2. So here 1 and 2. Here the first point. Let me make it here. Circle. 1 and 2. So first point is here. Okay. Second point, 2 and 3. 1, 2, and 3. So around here. Okay, now 3 and 4. 1, 2, 3, and 4.